Hi. So thanks, Doug. I'm Germán Delbianco from India Software Institute in Madrid. I will be speaking about the joint work. This is with Alex, my advisor, Anindya, also from India, and Ilya, who is around from now at UCL. So it says concurrent data structures link in time. So what's this? I'm going to be speaking today about specifying and verifying concurrent objects in a program logic that is called FCSL. And what we are advocating in this paper is a new technique that we call linking in time to reason with concurrent fine-grained objects that have really complex linearization points. And the key idea is really simple. Linearization points are pointers allocated in time. So what I mean with this, apparently this didn't go very well. The idea is that we are going to encode something that looks like a linearization order of the data structure as just another piece of auxiliary state in a concurrent separation-like logic. And this is going to imply that we can deal with all the corner cases of linearizability simply as if they are pointer-like manipulations on some abstract heap of the shared results, like a ghost state that will be erased after verification. And one interesting remark about this is this is implemented off the shelf in FCSL. So we have this logic, we have it for 4 years, and we are using it for really cool things that we maybe didn't thought at the beginning that were possible to do in the logic, without modifying the logic, and this is important message here. So I'm going to speak today, like we have this case study, it's a tricky snapshot algorithm example. I'm not going to say much about the logic. There's some other paper for that, so I'm going to give you an intuition on how this case study is difficult and how you build this auxiliary state in FCSL without going into the code, of course. So what is a concurrent snapshot, right? A concurrent snapshot is a fine-grained contained piece of memory. You can see like an array, like the two-pointer array. And the idea is that you have wait-free write and scan methods, right? There's no synchronization, no locking whatsoever. And the idea, of course, is write just writes, and scan returns you a snapshot, which is a view of the contents of each of the cells of this container at a definite moment in time. So an interesting thing about the snapshots is that this is inherently a concurrent problem, because since you cannot do this scan atomically, you have to, all the problems, all the complexity of reasoning with this thing comes from the interleavings of writes that may mess with your scan as you go on, right? And there are several snapshot algorithms around, and we are going to focus on this one, which is not particularly simple, but it looks short at least. This was introduced by Prasad Jayanti at this talk in 2005, and the interesting thing there at the beginning was that it was optimal. It was the first optimal scan where the complexity was on the linear size of the memory. For us, it's going to be interesting because it's really showcasing all these interesting things about complex linearizability. So how this goes? This has two memories, objects, right? The main, okay. This is not working, sorry. Okay. Oh, I was here. So we'll point with my hand. The memory A is the main object, like the one we are taking a snapshot. There's a control bit S, and there's a backup B, which is a copy of maybe values. You see some bottoms there. And the intuition, I will say that this is a single scanner writer version. There are several versions, and this has some consequences, but I will go over that further. So write, first writes to the memory, then checks the status of the scanner bit, and then decides where to copy or not this value into the memory. And you notice that this is controlled by the scanner, right? So the write method only reads S. So how does a scan work? The idea is that this is a two-phase scan, and where if you have missed a value in the first step, you are going to recognize it later because it's in a non-bottom value, and you will recover these failures. And in a little bit more detail, this goes with this particular two phases. So the first phase, like I said before, this prelude, you erase the backup, and you do the read, right? So you set this thing to saying, okay, I'm on the other side. Now the writers cannot write to B, so if I scan B, and if there's some non-bottom value, it should have been a new value written after line 5 of the scanner. So that's a value that was conflicting my snapshot. I update it, and voila, this should work, right? Well, you don't look that. All right, so we do some examples. We do some small clients, and we realize that you can construct a history in where it actually returns something that was never a snapshot in memory. So you're saying, what? So you start reading the paper, look for something that says theorem. This maybe have something. I say, okay, magic word, linearizable. So what linearizability means here is that when always you have this history, you could have built a history for that value, what it is not in memory but could have been, by doing the linearization of the methods into this atomic sequential history, when now you see that reading 2.1 was actually valid. So if you can do it for all these histories, then you prove that it's linearizable. So now how you do that? Well, the original proof, and it's something that is usually gone down when you're doing linearizability, is you have to find out linearization points, right? These atomic moments on time where I can shrink all the method into one atomic transition, right? So we'll just keep reading the paper. We reach the appendix in the last page, and we find this ugly definition of linearization points, which I don't want you to read. I have already suffered this, so I will try to explain. It's actually saying that, first of all, there's a good thing. The scanner always linearizes to the moment it changes phases. And the right, if the universe is a nice place, is always there at the moment that you suspect when it wrote to main memory. But it may mean that if there are these misses and new values that are conflicting, it could be everywhere, like literally everywhere here, or it could be in the scanner code after the switch of the phase, which is kind of weird. So, and what does this mean? This means, like in linearizability parlance, that this is non-fixed linearization point. It's determined by dynamic information. It's non-local because it might be on the scanner, and it's also future dependent, which means that it is determined by scan for write after its write has finished, right? So usually the logics that deal with things require some things like prophecy variables, a specific meta theory for speculation, and our message today is you don't need that. So I'm going to show you how to build the auxiliary state without a specific meta theory for speculation that allows you to do it in our logic. So we start with very basic things. We are going to draw the auxiliary state. So we have atomic write events, which is symbol where the write happened. And we're going to use these colors to encode the dynamic nature, right? So green means the order is settled. Yellow means I don't know. Red means I shouldn't be reading this. Now it's something usually happening with this kind of things. We are going to use histories to track time, but we are using FCSL. So we have these subjective histories, which means that we can pinpoint which histories are belonging to the thread and which ones belong to the environment, and it gives us this nice compositionality about the logic and reasoning with resources. There's more details in the other papers. But the new thing here is that we are going to detach the order from the order of the histories. So we are going to see this allocation in time, this logical order, and we are going to reserve us the right to change this logical order atomically to justify something that is not a snapshot that could have been. So if we identify some pointer that is wrong, like this yellow thingy, we are going to do this atomically and say, that's it. We cheat you, and now we are giving you a snapshot, and we change the justification for it. And that's the whole business of the idea. And I couldn't my talk here, but I will give you some intuition how you formalize this and get the spec. So first thing you know is try to put invariants to the auxiliary state. I'm going to give you a few invariants. So one kind of invariance is identifying which things you need to change. So we have these nice grammars, these patterns reasoning about colors. For instance, here you're saying that for each cell, you have this regular grammar that said you have many greens, one yellow, because you only can change one per pointer, and then many reds that you can ignore. And this allows you to kind of refine the state of the transition system into where you are. And more importantly, you have the things like you don't need to change. And so you take this idea from linearizability of taking the end times of the events, and we are going to encode a restriction that says if things were sequentially executed and they were not overlapping, you don't change them. And this is like the essence of linearizability, but it's not something that it's baked into our logic, but it's rather like just another invariant that in FCSL is part of the auxiliary state of a given resource. And we have done this in the past, actually, so we can compose objects that have different consistency criteria into the same clients by doing this business of using the same logical framework and then using this consistency criteria not as part of the logic, but as part of the object you are specifying. You can see Ilya's last year paper about that. But here, linearizability is just a property. And the next step is adding, auxiliary code. So we add some auxiliary code to scan, but I was saying before, the key thing is going to happen here, that you fix the order before return. In the previous example, this is you would see how the history would look in the example I was showing before, where you have like a run scan. And the idea is that you will identify this yellow thing, that conflicting things with all the yellow. You say, oh, this is messing with my snapshot. This is not valid. I will change it. And of course, now I have to prove that all of these invariants are satisfied, right? So that's all the requirements that you do have to prove in the system. There's all this soundly down in COC about that this is valid snapshot and all these invariants have been preserved. So now we go to the final stage that says, okay, how we reason with these things, how we build out of this. We have developed this auxiliary state that allows you to track these changes in the order of events, how that shows up to specs. So the first thing we notice is that this order is changing. So we want to hide it for the clients. We don't want to tell clients of the data structure that we are actually using these changes. So what we do is we create this abstraction that we call the stable dynamical order, which is the guarantees that you get about the order of events. And this is going to be defined as the union of these orders, and is thinking that, of course, things that were not overlapping will permanently sort it, like lifting the definition that we had before. And also we are going to say that all events that are green are fixed on the left, right? So these are settled by the scanner. They might be jumped by a previous yellow, but their relative orders on the left are set. How you use this in specs. So what's the spec that we can give for right? So I was saying before, these are subjective histories. You will see that these S and O variables, which means self-contribution and other contribution here. So we start with an entity self-history, so this allows you through framing to enlarge it. And in the post-condition, you notice there are primes, so you are using BDM notation where you can refer to the getters, these Greek letters in the precondition without the primes, in the post-condition with the primes. And it's saying that the new history has an entry for this right event. But, as I said before, the order may not be settled. So you cannot put T in omega prime, so you are using this downward restriction on this order, saying, okay, T is not in the new order, but it's still giving me a guarantee that it's going to be settled, this order will be going to be somewhere which is after the environment histories, all the XO, and this prefix that the scan has seen. So what this post-condition is saying, the order of right is not settled, but it's not messing with the existing linearization in a way. So let's look at scan. Scan similarly starts with an empty history. We are not tracking scan events. But we are getting that there's a timestamp that determines a snapshot. This is given by saying, okay, the result, the R snapshot that we are getting, is evaluated from omega and chi, and it uniquely determines a snapshot. This snapshot is fresh, and now it's included in this order. So it's saying, okay, I'm taking everything that existed before in the histories, and I'm considering for the scanner now. It may be new, it may be old. It depends on when the writes are interleaving. And also, this new thing is in this scan set. This scan set is something that I haven't defined, but it's kept, abstract to the clients. You can reason in terms of the properties of scan. So we hide this definition of what scan means. And scan means that these prefixes of the order of omega actually matches the prefixes of the internal history of the data structure. And moreover, everything in that prefix is green. So everything is settled. This means that scan omega is actually the linearization of the data structure. And when you look at the specs altogether, you are using the fact that this scan, you are using the linearization of the data structure to say that right doesn't mess with the existing linearization, and some sort of progress property for scan saying that you increase the information of events that have been linearized by running this relink operation and scan. But notice that the clients don't know about linking in time, they know anything about the changing of the order, they're just reasoning this fairly simple, I would say that fairly simple concurrent specs that just say this is a snapshot and there are some order requirements. So this is everything I have today. There's more clients in the paper, there are more details in the paper, the technical aspect of FCSL in the paper and in others. But I guess I should have convinced you that reasoning about concurrent objects is tricky, especially if you're tracking linearization points. And we are advocating to use this shallow technique in a way of linking in time as an alternative to using meta theory specific for your logic, because this is good, gives you compositionality of different criteria and etc. And everything is mechanized in FCSL. That means we have a lot of cock proofs about this. And this is the first actual formal corrective proof of this algorithm, which I think it's worth it. And that's everything I have to say. So I take your questions. Oh, you have the logic there. Okay.
Reading through the proof of that Jayanti algorithm was led me to believe that the reason these things are so hard is people in their head actually declare and use all these ghost variables, and then they optimize them away because they don't actually count. I think a lot of algorithm designers do that. Should they stop doing it?
Maybe. I don't have like an insight into how to come up. So our surprise in this was that this is too complex. It must be broken. And apparently, after a lot of effort for my part into finishing these proofs, he was right. So this tricky linearization works. Maybe I have been suggested that there may be some simpler proof, perhaps, than his original idea. But still, I have to admire these brains that come up with this algorithm that actually work. So I don't know what to say to these people because they are brighter than me, I guess.
Right. The moral is that many people are too afraid to do anything that can't be trivially shown using linearization points. And this is a good example otherwise. Okay. So not a question, just a comment.
Hi, you mentioned that you're treating a version of the algorithm that just has a single writer.
Oh, yes. I will expand on that. This is
yes.
The first version of the algorithm, which is single scanner and single writer per memory cell. So you have overlapping writers on different memory cells, which are fine-grained and can screw with the snapshot, but there's no overlap on per cell basis. So there's two alternatives to the full Jayanti, let's say it. There's other examples of the snapshot algorithm in the paper. There's some other constructions we can do. But mostly we started with this because it was simpler. And also the other ones, there's even no informal proof. So at least we have here some statement we are trying to sort of replicate. Say, we know that it's true, so let's try to prove it. Thank you.